So now we're on to the second class that we're not going to be together. Cycle 10, day 5. This is on January 31st. Slide 33 is where we're at this point. The warm-up for today is on slide 34. Question says, how many square meters, talking about square meters, so again, or not again, I should say. So already we know that we're talking about area. How many square meters would be covered if the central angle is theta, covered by the sprinkler from number 69 on the homework, if it was 280 degrees, right? So if the central angle was 280 degrees, this is our given information. We can also draw a diagram. So 280 degrees, right? 280 degrees means this is 90, this is 180, this is 270, so 10 more than that, right? That's going to be our central angle of 280 degrees. And it's saying how many square meters would be covered if the sprinkler did that from that problem, right? So in order to answer that question, you have to know the radius from the problem that we did on number 69 from the homework. So the radius from that one, the radius that the sprinkler could cover was 15 meters, right? And the problem for number 69, it's at 140 degrees, right? And you had to find the area of the region. So essentially you would need to use the area of a sector formula. But now we change it up a bit, right? We have 280 degrees. So we know information about the area, we know our central angle and our radius. So if we look at our formulas, right, again, we know our central angle and our radius. We don't know the arc length, so we're not going to use this formula. We're going to use this one. So for our equation step, area is equal to 1/2 r squared theta. Our unknown step here is our area. We could say area of sector, or you could say area of the sprinkler, or the water that's covered by the sprinkler. Our substitution, we don't know the area. We know that the radius is 15, and we know our central angle is 280 degrees, right? We have to convert 280 degrees into radians. The degrees cancel out, right? We'll be left with 28 over 18 if we factor out a 10. 28 is divisible by 2. That would be 14, right? 18 divisible by 2 is 9, right? So in that case, we would have 14 over 9, just want to double check, right? So 28 divided by 2 would be 14, right? 18 divided by 2 would be 9. So that gives us 14 pi over 9. So that's going to go there. Then you're just going to simplify what you have here, right? So in terms of pi, we can simplify all of this stuff. So we'll have 1/2 of 15 squared. 15 squared is just going to be 225 multiplied by, so this is over 1, all multiplied by 14, pi over 9. So essentially what we have when we multiply everything out, 225 divided by 9 would give us 25. So 225 divided by 9 is going to be 25. The 2 can cancel out with the 14. The 2 becomes 1. The 14 becomes a 7. So we'll have 25 times 7. 175 pi square meters. That's your answer in terms of pi. Now, if you wanted to write that exactly, or sorry, in an estimated way, you would take 175 and multiply that by pi, and that would give you an approximation rounded to the nearest tenth of 549.8 square meters. And that answers the warm-up, and hopefully that answers a question that you had, if you had a question on number 69 from last night. Slide 35 starts talking about particle motion. So an object on this circle, right, it moves or rotates around this center point. So we could talk about a circular track that someone could run around, right? Or if you have a ball at the bottom of a cup and you're rotating it around the bottom of the circle, right? Then we can talk about particle motion, right, as it perfectly rotates. We couldn't really use planets as much because planets have a elliptical orbit rather than a circular orbit. But it says the movement of an object at a constant speed in a circular path. So that's particle motion. Speed, v, is the arc length, s, divided by time, t, right? So we should remember that speed is always going to be distance over time. And since we're talking about a particle moving around the outside of a circle, that would be your arc length. So the distance is always going to be your arc length. So if you want to remember how to figure out the speed, it's always your arc length divided by your time. And also remember that your arc length can be calculated by taking your radius and multiplying it by theta. So that's important to remember. Now, angular speed, that's talking about how many radians you cover in a certain amount of seconds. So if your object is moving, right, you're moving and you're creating sort of a changing angle as you move around, right? So how many radians you cover in a certain amount of time, right, is going to be your angular speed. And this is also going to be something that's constant, so something that's not changing. Your angular speed is just going to be how many radians you travel, right? Your angle, or the radians traveled, divided by the time, right? So it's pretty intuitive. And we'll go over how to use these in actual problems. It says the speed and angular speed are related by this. So if we have your speed traveled, that's going to equal s over t. We know that. We also know that s is equal to r theta. So you could always replace s with r theta. So you could also say that speed is equal to r times theta over t. And we know theta over t is equal to your angular speed. Okay? So your angular speed here, if you multiplied it by r, right, that's going to be, whenever you write this, so it's a little bit of a typo, but it should be r times pi over theta, which is r times that Greek symbol, okay? Now that symbol is the Greek letter omega. So we've been talking about a couple of different Greek letters, right? We talked about alpha the other day. We talked about beta. We've talked about theta. And now we have omega, right? But again, don't be scared of these letters. They're just using a different alphabet rather than our alphabet. So they're just variables, right? A value could be equal to any of these things. So let's move on to slide 36. Example 1. It says an ant stays on top of the second hand of a clock as it moves. So we can draw a little ant if we want. Right, so there's our ant, right? He's going to stay on the top of this second hand as it moves. If the second hand is 8 centimeters long, right? So this second hand right here is 8 centimeters long, right? That would represent the radius of our circle, right? Find the linear speed, right? So not talking about angular speed, linear speed. So that means we're looking for our v, right? Our linear speed, not our angular speed, of the ant in centimeters per hour. And what I mean by linear speed versus angular speed, right? We're talking about how far is this ant traveling if we could map it out on a linear plane, right? If we could say that this ant is starting at one point here, right? And as it covers distance, even though it's circular, if we could map it out in one straight line, right? That's the distance that we're looking for that has been traveled. But we also want to know the speed that it's traveling as it goes from one point to the other point. So for our linear speed, right, we need v, and our formula for speed, remember, is going to be your distance traveled over the time that's traveled. Now, the distance that traveled is your arc length, right? So as he moves around, we're moving centimeters per hour, right? So that's something easy to remember. He's traveling around, right, this clock and getting back to here, and that's a certain distance that's traveled, right? That would be his arc length, or his s, right? We know that s is equal to our radius times our theta, our angle that's covered. So our linear speed is going to be r theta over our time, right? We're talking about 1 hour. And so our radius is 8. Now the angle that's covered, right? In an hour, right? So how many radians are covered in an hour? Well, we know every minute we're covering a full revolution of radians. So in 1 minute, we're traveling 2 pi radians. But that's just 1 minute, right? An hour is 60. So we need to multiply that by 60. So 60 times 2, that gives us 120 pi radians in an hour, right? So we're going to multiply our radius times 120 pi radians every 1 hour. So we're talking about now 8 centimeters per hour. And then we just multiply what we have here. So 8 times 120 gives us 960. So our linear speed is 960 pi centimeters per hour. That's our exact answer. Now, if we wanted to find out what that is as a decimal, we just multiply 960 by pi. And this ant is covering 3,015 point, we'll round to the nearest tenth, because that's what we've been doing so far today. 3,015.9 centimeters every hour, right? Which sounds like a lot, but this is centimeters, right? And it takes a whole hour. And each time he's going around, he's covering a certain amount of distance, right? We could divide that by 60 and figure out that he's traveling 50.3 centimeters, right? So if we divide that by 60, that's about 50.3 centimeters every minute. And remember, he's not actually doing the work, right? It's the second hand that's doing the work. So that's how he's traveling. So our question says, find the linear speed. So our linear speed would be 960 pi centimeters per hour. Or if we wanted to approximate it, we could say that that's about 3,015.9 centimeters per hour. Now for our last example, it says the circular blade on a saw. So hopefully you can see that in this picture. And on the actual document online, it's a GIF. So it'll show you that this blade is spinning, right? So here's the center of the blade, right? Here's our circular blade. And there's the center. So there's our circle. It rotates at 2,400 revolutions per minute, right? So that means that a particular point, or a particle, right, is moving at 2,400 revolutions. So it's completing one revolution 2,400 times every minute. So it says find the angular speed of the blade in radians per minute. Okay, so we need to figure out it in radians per minute. So remember, angular speed is just the radians that are traveled and the time that is traveled in. So our angular speed, or omega, is equal to theta over t. Now you'll notice in here, it doesn't tell you what theta is, right? It doesn't tell you how many radians are covered. But it does tell us that it's going around 2,400 times. Well, we know that every rotation is a certain amount of radians, right? So every rotation, we're going to be covering 2 pi radians. So 2,400 multiplied by 2 pi, that's going to be a total of 4,800 pi radians per minute. And that essentially answers our question, right? Because we know that the time is minutes. So that's how many radians we're covering, right? And we're traveling this every minute. So there's our answer. So it's easier than you think. It says now, if the blade has a radius of 4 inches, find the linear speed of the tip of the blade, right? So we've covered how many radians that this blade is going to cover every single minute. But now we want to figure out what is the linear speed. So remember, linear speed was v is equal to your arc length over your time, right? So what is the arc length? Now, the arc length in this particular problem would mean if you start here, to figure out the arc length, you would have to find out what is the distance around the circle, right? And do that 2,400 times, right? Whatever you find out is your distance around your circle, or essentially your circumference, you'd multiply that by 2,400, and that would be your arc length, right? But we know information about the arc length, right? We know that the radius times theta is always equal to your arc length, right? So our radius that we can substitute in is given to us right here is 4 inches. So let's say that we have a radius of 4 inches, and just for clarity, I'll leave this as 4 for now. And the theta that's covered, right, we know that in that amount of time, we're covering 4,800 pi radians every minute. And then we're going to divide that by the time, right, which we are looking for the linear speed. So that's 1 minute. So essentially we're going to convert this, or we're going to just multiply. So we can multiply 4 times 4,800 and get 19,200. Inches per minute, right? So that's a lot of inches, right, every minute. So if we were to approximate that, right, we would multiply that number by pi. So that's going to be approximately 60,318.6 inches per minute. And if we wanted to write that in terms of hours, right, if it's traveling this amount every minute, right, to figure out how it's traveling per hour, you could just multiply that by 60, right? Or if you're trying to figure out the speed of it every second, just divide that by 60. So let's actually do that. If we divide that by 60, we figure out that every second, the blade is traveling 1,005 inches, right? So that's very fast. And just to make sure that that makes sense in terms of how you could actually talk about that, right? Normally we talk about speed in terms of miles per hour. So right now we have it down to inches per second, right? So if I wanted to figure out what this was in terms of feet per second, right, I would just take 1,005 and divide that by 12, right? So that's approximately, if we divide this by 12, that would be approximately 83.8 feet per second, right? So if we wanted to figure out, well, how many feet is it traveling per minute? We would multiply that by 60, right? That will give us something that we would have to multiply by 60 again in order to get it into hours, right? So essentially we would be traveling 301,500 feet per hour, right? Which sounds like a lot, but if you divide that by 5,280 feet, right, that's going to give you how many miles you have, which is 57 miles per hour, right? Which, if you look at a blade on a saw, right, it is going very fast, right? So it's going at 57 miles per hour. So that's how you can look at this. So if a problem that you work on ever asks you to write this in different units, just think about how you would convert it in science class with trying to get rid of the units, and do the same thing as we did just there. And your last homework will be from Trig 1.1, numbers 51 through 57, odd 63 through 66, and number 70. You're going to have a trig formative on 1.1, but don't worry, we will definitely have time to answer your questions if you have any.